I can.
It is a pleasure for me to introduce Setiawan Wenming. He did his PhD at the University of Maryland, and he's currently a postdoc in Ash Clerk's group at U Chicago. And he's going to talk to us about high-fidelity quantum gate via accelerated adiabatic evolution, and we're looking forward to his talk. Take it away. It's your show, man.
Thank you, Dr. Santiago, for the introduction. So let me share the screen. Okay, I hope you all can see my screen.
Yes, we can. It's not on presentation mode, though, and now it is.
Yeah. Okay, yeah. Okay, thanks a lot for the invitations to give a talk in this HUT colloquium. I'm happy to share my work with you all. So today I'm going to talk about a different approach to design high-fidelity gates in superconducting circuits. So the idea here is basically we are going to use the so-called shortcuts to adiabaticity.
This is something related to research.
Yeah. Yes.
Oh, quantum stuff? Yeah. So one thing is they happen at the same time. So this is maybe the best feature of Zoom.
Okay, so should I continue? Okay, so yeah. Is there any question?
I don't know how that happened. So maybe they enable this feature.
Jimmy Yao, please mute yourself.
Okay, so yeah. Okay, I thought it was a question. So okay, okay. So basically, I'm going to use the so-called shortcuts to adiabaticity or accelerated adiabatic approach to design a high-fidelity gates in superconducting circuits. So this shortcut to adiabaticity is basically a different or alternate methodology where we use non-computational states as a resource to design gates. On the surface, it looks an attractive approach, where it gives us the ability to analytically design the pulse on one hand, and on the other hand, it also gives us a balance or trade-off between robustness and speed. But most of the ideas of using these shortcuts to adiabaticity in the literature only consider simplified C settings where we only consider few level, and also we make an extreme rotating wave approximations. So the question here is that the advantages of the shortcuts to adiabaticity still holds when we consider a more realistic setting where we have many non-computational states. And here in this talk, I'm going to address this problem concretely. I will give you a detailed theoretical analysis of how to use this shortcut to adiabaticity approach to design a high-fidelity gate in the superconducting fluxonium circuit. And I would like to emphasize though, even though here I'll focus on a specific setting, which is heavy fluxonium, our idea is actually general and can be used to for a variety of different systems. And our work here is published recently in this journal. You can look at it if you want to know about the details. Okay, so before I start my talk, let me begin by thanking my collaborator. I would like to thank my colleague, Peter Groskowski, who is also a postdoc in ASH Group, Hugo Ribeiro, who is ASH former postdoc, and he's going to move to UMass Lowell to assume a faculty position. And lastly, I'd like to thank my advisor, Ash Clark. And okay, so let me begin by a very general motivations. So we all know that superconducting circuits are not two-level systems. It has many levels, and there are also many non-computational levels. So these non-computational levels actually can be used as resource to design high-fidelity gates. Perhaps the most famous gates that use this kind of idea is the 2-qubit gate for frequency tunable transmons, where we have here the computational states 1, 1, where each of the transmon are in state 1, and is driven rationally to non-computational state 0, 2. And the idea of using non-computational states can also be applied for 2-qubit gate in fixed frequency coupled fluxonium, where here we drive the 1, 1 and 2, 1 transitions. And if you drive the transition such that the population is transferred from 1, 1 to 2, 1 and back, then we can imprint a phase on 1, 1. In that case, then we can get a CZ gate. However, this normally, if you use this kind of non-computational states, there's a drawback. So it is because these non-computational states are high in energy, so it normally has high level of dissipation compared to the qubit level, which can degrade your gate performance. So the question here is that, can we use it in another way such that we can avoid these common drawbacks? Of course, you can use it in a non-resonant way, is in a detuned way like Raman, but it comes at a price that the gate will be very slow. Hence, it will be subjected to dissipation. So really here, we would like to have another approach that overcomes all of these limitations. So the starting point is a procedure which is well known in atomic physics and quantum optics, which is called STIRAP. And this STIRAP process, basically using these simple lambda configurations. So where in this lambda system, we have 2 lower states, which I call 0 and 1. They do not have direct coupling with each other, and they talk to each other only via a common excited state. So we can here transfer the protocol, the state from 0 to 1 by using a time-dependent field that couple the state 0 and E, and also another time-dependent field that couple 1 to E. And basically, in this STIRAP protocol, which we are going to use to transfer the state from 0 to 1, there exists an adiabatic dark state. And when these 2 pulses are on, the adiabatic dark state can be expressed as a linear superposition of the 0 and 1. And it does not involve the state E at all. So by tuning on and off the 2 pulses in a counterintuitive sequence, we can then tune the dark adiabatic states from all 0 to all 1. So in this way, we can then do a state transfer from 0 to 1. By counterintuitive sequence, what I mean is that, so suppose we have the initial state at 0 and we want it to move it to 1. So what you need to do is to first turn on the pulse that drive these 1E transitions, and then you slowly turn it off while turning on the pulse that drive the transition between 0 and E. And this is the example of the pulse. And so at the end, you have the population which is at 0 being transferred to 1. And note that during the whole protocol, the state E is never populated, which means that the STIRAP protocol here is robust or insensitive to the loss or dissipation of the E level, the excited level. Moreover, it has another advantage, which is that it is robust against parameter variations. You do not need precise tuning of the pulse area to do this state transfer. And it is also useful for protected qubits, where you do not have direct coupling between 0 and 1. So note that this is different from the Raman scheme, because for the Raman scheme, actually the pulse here is detuned from the transition, while here we drive it on resonant to the transitions. Okay, so far so good. So there are catches here. So the first catch is that this STIRAP is just a state transfer. It's not a gate. So the question is how to make this into a gate. And the second catch is that the beautiful physics that we just talked about only holds in the adiabatic regime when the gate time is much larger than the time set by the scale of the pulse amplitude. Okay, so before we address this challenge, let us see how can we find this kind of lambda system. So this lambda system can be engineered in different kind of superconducting qubits. For example, in fluxoniums, 0 pi qubit, or transmon cavity transmon system. Normally, in this kind of system, you have different, for example, here different wells, where the ground states in each well can be used as the lower state of the lambda system, with a common, which is driven to a common excited state. And this kind of potential well is normally good to get a T1 protected qubit, because the qubit states are isolated from each other. So there is difficult to drive transitions between the logical states, and the lambda system or the STIRAP gate that we talk about is useful. And as we said just now, STIRAP is not a gate, it's just a state transfer. So the question is how to turn it into a gate. So the idea actually has been worked out many years ago in the context of trapped ion. And basically here, we just need to enlarge our lambda system a little bit by adding in another state, which I call A here. And this auxiliary state is also coupled to the same excited state. So here we have then a 3 lower level, which do not have direct coupling between each other, but they are coupled to a common excited state, which form the so-called tripod structure. By picking the pulse amplitudes in the right way, you can then have a tailor-made lambda system. And you can now use this lambda system to perform a double STIRAP to get a single qubit gate. So what you need to do is now to do the STIRAP twice. So so in this double STIRAP process, what you have is the 1 tilde state will then move to A, and then at the end of the day, the population will be moved back to 1. So since it's a cyclic evolution, at the end of the day, you will get this geometric phase encoded in 1 tilde. And this 1 tilde here is a linear superposition of your original qubit state 0 and 1, where the relative strength here is governed by the relative strength of the pulse amplitudes. So in principle, then this geometric phase will give rise to an arbitrary single qubit gate. However, again, the beautiful physics that we talked about here only holds up in the adiabatic regime when the gate time is much larger than the time set by the scale of your pulse amplitude. So the questions or the challenge here is, how can we make this, how can we still do the STIRAP protocol while not having to do it in an infinitely slow way? So we can then use the idea from shortcuts to adiabaticity. So here is a simple cartoon that I used to illustrate the shortcuts to adiabaticity. The box represents the Hilbert space. So if you try to do the gate that I just talked about faster and faster without any corrections, basically you will accumulate non-adiabatic errors, which kick you out from the dark adiabatic state that you want to stay in. So the idea of shortcuts to adiabaticity is that you find a dry state which allow you to deviate from the dark state in the intermediate time, but you will come back to the state that you want at the end of the protocol. So there are a lot of shortcut to adiabatic state protocol, but the problem that we have here is a little bit different from what we normally think about. So a generic shortcuts to adiabatic state protocol cannot be used for this problem, because not only we need to cancel the non-adiabatic errors, we also need to preserve the geometric phase that we use for the single qubit gate. But however, they can use a version of the shortcut to adiabaticity, which is called super adiabatic transitionless driving, or SATD in short. And this version of shortcuts to adiabaticity allows you to completely cancel the non-adiabatic errors while preserving the adiabatic phase. And these SATD corrections only entails modifications of your path envelope. And this modification can actually be described analytically. So to do the non-adiabatic corrections here using the SATD protocol, basically you do not need any extra couplings or extra tones. So here, yeah, as we have just said, adiabatic protocols are slow, so we can speed it up using the SATD approach, which completely suppresses the non-adiabatic errors, and it can be described using an analytical form. And basically, the SATD corrections tell you how to change your path envelope, and this is what the figure here shows you. So suppose you are in the adiabatic regime where you have large omega naught Tg, then your path will look like what we have here for the green curve. If you move away from the adiabatic regime, basically you need to cancel the non-adiabatic error, and you can do that by putting in more and more SATD corrections to your path envelope. And the nice thing about the SATD correction is that all of these can be done analytically. And so we have seen how to build or how to design an SATD protocol that cancel the non-adiabatic errors for few level systems. The question is, we know that superconducting circuit is not just a 2 or 4 level system. It has many, many levels. And these additional levels can give rise to current errors, which can degrade your gate performance. It also, for this tripod gate, it also have a drive crosstalk that you need to worry about. What I mean by drive crosstalk is that suppose we take this omega naught E pulse as an example. This omega naught E pulse is supposed to drive only the transition between 0 and E. However, realistically, it can also drive the 1E transition and the AE transition, which can then give rise to additional current errors. And in realistic systems, we also need to take into account dissipations. So the question here is that, can we still use the SATD pulse that we designed for few level systems and get the and have the advantage preserved for this when you apply it to the realistic systems with many levels? So to answer this question, I'll just then focus on a specific system, which is a T1 protected heavy fluxonium. A fluxonium is basically a Josephson junction, which is surrounded by a capacitor and inductor, and it has a potential landscape as a function of phase shown in this picture here. So basically, it has a cosine potential that rides on a parabola. We can use the fluxon levels, which is localized on each well as the lower level of the tripod. And then we can use the central plasma level as the common excited state, where we can drive in order to our tripod gate. But notice that here, besides these 4 levels, there are also other levels which are colored in gray. And these levels can give rise to current errors. So our tripod is actually far from being ideal. So you can ask the question is about what is actually an ideal tripod. An ideal tripod is a tripod that only have 4 levels and also do not have direct coupling between the lowest levels, and also good coupling between the ground states and the excited state. So to have this kind of tripod, we have then to work in the regime where we have small inductance energy, such that we have a small overlap between the qubit states. And moreover, we also need a delocalized E level that is delocalized here over the 3 wells, such that the coupling between the lower levels and the excited level is large. We can perform a numerical search to identify optimal parameters, and this is the parameters that we get. We have here the qubit transition matrix elements about 2%, but here we have the tripod matrix elements for these 3 transitions, not that large, which is only, the smallest one is only 8 times larger. So despite our best attempt to identify optimal parameters, our tripod is actually far from being ideal. However, as I will show you, even though we do not have the work,
are the absolute values of the parameters important, or is the ratio?
Only the ratio is important. Yes, this is actually the absolute value. Yeah, so the phase that is not important. Yeah, thanks for the questions. So if you have any question, please feel free to interrupt me. So the upshot here is that even though our tripod is far from being ideal, as I will show you, we can still get a very good gate fidelity. Okay, so see this, let us first focus on the simplified model where we only consider 4 levels and we ignore all the non-RWA processes. But here we will include dephasing for each level. And what we have here is the state average gate error for an X gate as a function of gate time Tg. So, and the orange curve is the gate error that you get if you use the pulse, the adiabatic pulse without any SATD corrections, which work perfectly fine in the long gate time limit or in the adiabatic regime. And not surprisingly, as you go to a shorter and shorter gate time, or you do your gate faster and faster, there will be non-adiabatic errors that degrades your gate performance. And the red curve here is the gate obtained by using the SAT corrections by changing your pulse envelope in analytical way so as to cancel the non-adiabatic error. So in principle, you can go to arbitrarily fast and having a small error by using this SATD pulse. And the error here is only due to the dephasing. And for one thing that come out from this simplified model is that for each gate time, if you pick a particular gate time, there are in principle infinite number of SATD protocols that you can use. So each protocol here will be characterized by omega naught, which is the pulse amplitude of your adiabatic original pulse. So whatever value of omega naught that you pick, there is a corresponding perfect SATD protocol that you can use to correct for the non-adiabatic errors. And I will show you later on that you can use this degeneracy of perfect protocols to further mitigate the current errors due to the extra levels that we need to consider. Okay, so here is how it works. So again, we pick a decide time Tg, and if you now pick your omega naught, which is the scale of your pulse amplitude, very large, then you are basically in the adiabatic limit. So you do not need to do any pulse shaping to correct for the non-adiabatic errors. However, if you are picking a value of omega naught, which is not too large, then you need to do some pulse shaping in order to correct for the non-adiabatic errors. So in principle, there are many of them, because each of them is characterized by a value of omega naught, and they are equally well in the sense that you can cancel perfectly the non-adiabatic errors if you consider just these 4-level models. This degeneracy of perfect protocols will be lost when you go to the realistic system with many levels. However, we can use this degeneracy of protocols to cancel the current errors due to the non-RWA process and the extra levels. So the idea is very simple. So the current errors due to these extra levels or non-RWA processes basically gets worse as your pulse amplitude gets larger. So what you need to do is then to pick a protocol among the so many protocols that we have that minimizes some sort of measure of the energy of the protocol. For example, the drive power or the RMS voltage. And the optimization here is easy to do as well, because all the pulse here can be described analytically. So if you optimize it, you will end up with this value of omega naught that gives you the minimum driving power. So the upshot here is that using this optimal power power efficient protocol, basically we can minimize the current error. And our optimized power efficient protocol actually has a speed which is close to the quantum speed limit, which is very nice. Okay, so we have now a simple way to mitigate or minimize the current errors, but actually we can do more. We can also correct for the current errors using perturbative corrections. For example, we can use the Magnus-based approach. And one can think about this Magnus-based approach as the standard drag approach that people use normally to cancel for current errors due to leakage levels or other non-RWA processes. And this Magnus-based approach will tell you a further analytical corrections to your pulse envelope in order to minimize the to mitigate the current errors. And it also tells you how you can chirp your frequency in such a way that you can further minimize the current errors. So here is the idea. So we already have the SATD pulse that we use for simple few level systems where we correct for the non-adiabatic errors, and we can build on top of it the Magnus corrections, which further correct for further modify the pulse envelope and introduce a time-dependent chirp which mitigate the current errors. And here I have the summary of the approach that we use to design the high fidelity tripod gates in realistic system. We first start off with the SATD protocols for few level systems where we have in general infinite of them, and all of them can cancel perfectly the non-adiabatic errors. And then we can pick the one that optimizes the driving power, which optimizes or minimizes the current errors. And we can further correct for the current errors by using Magnus-based approach. And this Magnus-based approach will tell you analytically how to modify your pulse envelope and also chirp your frequency. Okay, let's see how this pulse here performed. So here is the results. Again, is the plot of standard state average gate error versus gate time. And here is the result obtained from a full numerical master equation simulations by including 18 lowest level of the fluxonium. And we also take into account all the non-RWA processes. So we are not really throwing away any complexities associated with the system. And we also include the most dominant error dissipation channel, which is the 1/f flux noise dissipations. So as you can see here, in the short gate time limit, the error is limited by the coherent errors. And in the long gate time limit, we are limited by the dephasing. But there exists a sweet spot around 100 nanoseconds where we can still have a decent performance. The fidelity here about 3 nines. So one thing that I'd like to emphasize here is that despite our tripod here is far from being ideal, we can still have very good gate performance. And we can make a comparison of this gate to gate which is done on similar system. And there's a nice paper by Jens Kohl and Dave Schuster, which uses numerical optimal control on similar heavy fluxonium with similar device parameter. And they get a comparable fidelity that we have here. But the nice thing here that we have is that we do it analytically, and then the gates that we have also give rise to a good good fidelity. And you may now,
Setiawan, I have a quick question. So I'm trying to reconcile this dephasing time with this gate time infidelity. So is it reasonable to say that there's some kind of dynamical decoupling that's going on, that you're kind of insensitive to this 1 over f noise?
No, I'm not insensitive to 1 over f noise. So that's why here you can see that as the gate time is larger and larger, you have more and more errors. And this error here is actually due to the 1 over f flux noise that in the system. However, in the short gate time regime, the error due to dephasing is small. So what is dominant here is the coherent errors. The error due to the fact that you drive the system with high power, and that also drive the back transitions, which give rise to the coherent errors.
Right, I understand this. I was just looking at the ratio of your gate time to the dephasing time, and it's just kind of surprising that you could get such a high fidelity in that case.
So yeah, so here is 7 microseconds, and here is 100 nanoseconds. So in principle, it's still very small, the ratio. So yeah.
All right, thank you.
Yeah. Yeah, so you can also ask about how this gate compared to a gate that you can do by directly driving the 0-1 transition. So in principle, yeah, here again we have a small matrix element between the state 0 and 1. However, if you drive it hard enough, you can still perform the X gate. And this is what this blue curve shows. So at first, it seems depressing that the direct driving gate seems to do better than the tripod gate at all time. And one thing to note here is that there's not much difference between the two errors, the gate errors, and that can be understood by the fact that the qubit matrix transition matrix element here, which is 2%, is actually not much smaller than the smallest tripod transition matrix element. So the ratio here is only about 8. And so if you do the so this seemingly superior performance of the direct driving gate actually comes at a cost that it needs to use a larger power because it has a smaller matrix element. Indeed, for this case, we can characterize the power using the root mean square voltage, and the power used by the direct driving gate at the same gate time is actually 10 times larger than the power used in the SATD or the tripod gate. Now, if you can make the comparison a little bit different by comparing the two errors using the same power constraint. So what we have here is we have the gate time for the SATD or the tripod gate, and on the top here we have the gate time for the direct driving. which have the same power. So those time here, which is then be linked by a vertical line to this gate time, have the same direct drive, the same driving power. So as the result here, you can see that this SATD gate for the same driving power, actually SATD gate is faster by a factor of 3 compared to the direct driving. So which is why if you work in the dissipation limited region, your gate error for the SATD will be lower than
I'm gonna push back on the same question that Ravi asked.
Yeah.
I'm still confused about the fidelities because 100 nanoseconds over 7 microseconds, that's more than 1% just by coherence limited. So if you're getting better than 1%, we would like to see what you're doing to get better than 1%. That's above the numbers.
Yeah. So yeah,
100 nanoseconds over 7 microseconds is 1/70. So that's more than 1%.
Yes. Yeah. So what we have here is yeah. Okay, I see. So yes. So actually, yeah, I have a good question here. So the way we model the T5 here is not we normally think about. Okay, so maybe I'll show you how we model the T. I have a slide here. Okay, so basically what we do is, so the standard way to model the T5 is that you try to, so this is a 1/f noise. Basically, you try to approximate the Gaussian using the exponential curve. So what normally people do is that they just take this 1/T5 and 1/T5 and use it as the rate in the master equations. But actually, we can do a better job in approximating the Gaussian decay by an exponential decay. So what we imposed here is that we want the decay to be the same when for this Gaussian and this exponential decay when at the end of the gate protocol. So normally what people impose is that we want the decay to be the same at the end of the T5 itself, right? Now we are modeling it in a more precise way where we want the decay of the coherence to be the same for the Gaussian exponential curve to be the same at when you are done with the gate. And that's why here we have gamma, which is the decay, which is Tg divided by T5 squared, which is lower than the decay that you will get if you just simply take the case when you want to have the boundary condition where the decay for the exponential and Gaussian is the same at T5, not at the Tg. Do I answer your question? Yeah, obviously, if you just use what people normally have, right, which is gamma equals to 1/T5, you will not expect such a fidelity. But here our gamma is actually much lower than that, because our Tg is actually much smaller than T5. So our gamma here will be Tg/T5 smaller than what people normally have when they approximate the Gaussian decay by the exponential decay.
Yeah, I think I would have to think about it more, but let's go on. I don't know if Ravi wants to chime in and say anything else.
Yeah.
No, I'll have to also think about it more. Thanks, so.
Yeah, basically it's just due to how you approximate the Gaussian to the exponential decay. Yeah, when you are using these master equations, right? You need to somehow, you cannot simulate the Gaussian decay. So what you need to do is, at best, you use a rate that gives you the same decay at the end of T5, and you use then a rate which corresponds to an exponential decay. What we use here is still an exponential decay, but what we impose is that the decay here for the Gaussian and the exponential needs only be the same at the end of Tg, not at the end of T5. So that's why we have a lower rate. So so this is what we have when we compare the two gate errors when we impose the power constraint. So, and here we can see that we have the direct driving gates having a larger error than this SATD gate. But you can ask, why should we be limited by this power constraint? So imagine you drive your fluxonium via a cavity. So in such a system, then you like to have your cavity photon number not be larger than some threshold. So this limit on the photon number will then impose the limitation on the drive power for a given cavity qubit coupling. So which means here that it will restrict, it will give a limitation on how far you can go to the left. So in this power limited comparison, our SATD gate actually performs 5 times better than the direct driving gate. Okay, so I have shown you a different approach of designing high fidelity gates in superconducting circuits. So all it involves are just analytical. We do it in analytical way, and this the way that we do it cancel the non-adiabatic errors and then also the current errors that exist in realistic setting. And surprisingly, our gate is 3.2 times faster than the direct driving protocol for the same gate power. And we also get a very good performance in a very short gate time. So one interesting thing to think about is how to extend this work for a 2 qubit gate. And this is what we are doing now. And from our initial simulations, the work seems promising. We can still get a very good performance of the gate. So with this, I'd like to end my presentations, and thanks for your attention. And I welcome any questions.
Okay, thank you for a very good talk. Any questions from the team? Okay, if there are no questions, let's thank our speaker again, and thank you everyone for attending.
Thank you.